In the sky, where speeds break the sound barrier and every mistake can cost a life, why are cutting-edge combat machines held together by hundreds of thousands of tiny rivets instead of being welded into one solid piece? Is there a hidden technological secret behind those seemingly simple joints? In this video, we'll analyze rivet technology on modern fighter jets. First, let's understand what welding and riveting actually are. Welding is the process of heating the parts to be joined until they melt and fuse into a single unit. This method is low-cost, efficient, and one of the most widely used joining techniques in the world. Riveting, on the other hand, uses rivets to fasten two or more sheets of metal together. Holes are drilled into the panels, rivets are inserted, and a riveting gun flattens the tail end to lock the parts in place. It's the same idea as the scissors we use every day, which are also joined by rivets. Comparing the two methods, riveting relies on drilled holes and mechanical fasteners. Welding melts the contact area into a seamless block. Welding is faster and produces tighter seals than riveting. So why do fighter jets use rivets instead of welding? In aerospace, weight is always the greatest challenge. Even shaving off a few grams can help an aircraft fly farther, faster, and more efficiently while still maintaining full functionality. For that reason, engineers design the aircraft's outer skin to be extremely thin, often just about 2 millimeters. The usual materials are aluminum alloys or titanium alloys, both lightweight yet strong enough, but that thinness imposes extremely strict requirements on joining technology. Welding is almost unusable here because aluminum and titanium alloys handle heat poorly. Once welded, the skin is prone to warping and distortion. This is why the fuselage of aircraft cannot rely on welding. You might ask, but didn't the early MiG-25s use welding, and wasn't that fine? The MiG was born at the height of Cold War tensions. At that time, the US announced it was developing the SR-71 Blackbird, a reconnaissance jet that could fly at maximum speeds beyond Mach 3. That speed was beyond the reach of any conventional fighter. They couldn't catch it, let alone control it to monitor or intercept. Faced with this challenge, the Soviet Union immediately saw the need for a countermeasure. Military leaders decided in the shortest possible time they had to create an interceptor capable of surpassing the SR-71 in speed. And from that requirement, the MiG-25 development program was launched. To make an aircraft faster, the most straightforward and immediate solution is to install engines with greater thrust. But with extreme speed came a serious problem. As the airframe pushed through the atmosphere at hypersonic velocity, friction generated enormous heat across the entire surface. Given the materials technology of that era, the danger of the aircraft overheating to the point of deforming or even exploding mid-flight was extremely high. In the middle of this engineering deadlock, a bold proposal emerged: build the airframe out of stainless steel.
This idea immediately caused fierce controversy. The advantage of stainless steel is high heat resistance and excellent corrosion resistance, characteristics that are very necessary for hypersonic flight. But its downside is also obvious. When a huge stainless steel aircraft body rubs against the air at extremely high speeds, the heat generated is so terrible that the pilot could be roasted alive in the cockpit, even before reaching the stratosphere. However, under the harsh schedule pressure that Soviet leaders continuously shortened, the engineers had no other choice. They were forced to unanimously choose stainless steel as the main material for the MiG-25 airframe, while also designing a special cooling system for the cockpit. When flying at extreme speed, the outer surface temperature of the MiG-25 could exceed 1,000 degrees Celsius. Thanks to this cooling system, the air when led into the cockpit was lowered to about 50 to 70 degrees Celsius. However, note that a normal sauna only reaches about 45 degrees Celsius, which means that MiG-25 pilots were forced to work in hot conditions that almost tortured the body. In 1967, at the Domodedovo Air Show near Moscow, the Soviet Union for the first time publicly revealed the MiG-25. Flying continuously at an altitude of 24,000 meters, at a speed of Mach 2.8, and even reaching a maximum speed of Mach 3.2. This aircraft set more than 20 world records, notably the absolute altitude record of 37,650 meters set by pilot A.V. Fedotov on August 31, 1977. which is still in effect today. Of course, these brilliant achievements came at a price. According to documents, the engines of the MiG-25 after landing were completely damaged. The Tumansky R-15 engine was confirmed to be unable to withstand cruising speed at Mach 3.2. That was only a temporary limit speed. If flying long at that level, the engine could burn out or even explode. But in the eyes of the Soviet leaders, that price was nothing compared to the political meaning, surpassing the United States in hypersonic technology. Besides the MiG-25, to understand more clearly why welding technology was not a long-term solution, it is necessary to compare it with the very opponent it was created to counter, the American SR-71 Blackbird. The SR-71 began flying in 1964, famous for its ability to reach cruising speeds of Mach 3.2 at altitudes above 25,000 meters. The special point of this aircraft is that most of its body was made of titanium alloy, accounting for more than 80% of its structural weight. This was an extremely bold choice, because titanium is very difficult to process, expensive, and has scarce supply. In fact, the United States had to go through intermediary companies to import titanium from the Soviet Union itself to serve production. Meanwhile, the Soviet Union chose another path, using stainless steel for the MiG-25, a material that was easier to process, cheaper, and allowed mass production in a short time. The disadvantage was that it was too heavy, making the MiG-25, although very fast, less maneuverable with short range and low engine life. This contrast reflects two completely different design philosophies. The United States focused on advanced technology, accepting high costs in exchange for a sustainable long-term platform. That is why the SR-71 could maintain Mach 3 cruising speed without destroying its engines. The Soviet Union prioritized development speed and production numbers. They chose the solution that fit the technological context of the time to quickly reach higher speeds than their opponent, even if it meant sacrificing in other aspects.
More than 1,100 MiG-25s were built. Although they reached Mach 3 in testing, that speed was only a technical limit and could not be sustained for long. As a result, the SR-71 was almost untouchable throughout its service life, never shot down once. Meanwhile, although the MiG-25 set many speed records, it revealed many limitations in actual combat. This shows that using welded seams without pause was only a temporary solution. The sustainable path for military aviation was still reducing weight with titanium and aluminum alloys and precise riveted structures. So what are the advantages of rivet technology on fighter jets? There are three main points. First, it is not easy to deform the components. Today, even though advanced welding techniques like laser welding exist, with the same type of material, the thinner it is, the harder it is to process. The aircraft skin is only about 2 millimeters thick, so the welder's skill requirements are extremely strict. Just a tiny deviation in technique can create major errors, directly affecting mass production. In contrast, riveted joints depend less on individual skill and do not alter the metal's properties. Rivets are manufactured on industrial lines with micrometer-level precision. Thanks to that, efficiency in mass production and quality control is superior to welding. However, to implement riveting, engineers must design rivet layouts and pre-drill holes before assembly. Therefore, the preparation stage often takes more time compared to welding. Second, the working characteristics of fighter jets are always within structures that endure continuously changing loads. Welded joints often lose strength over time and risk forming micro cracks. If not detected and fixed in time, these cracks can develop into serious safety risks. In contrast, riveted joints can withstand very large forces, up to about 1,100 megapascals, equivalent to 11 tons on just 1 centimeter squared of area. In addition, riveted joints have outstanding advantages in fatigue resistance, vibration resistance, and preventing crack propagation. Thanks to this, the joint areas maintain high stability and can withstand harsh external conditions.
Third, convenient maintenance. The service life of a fighter jet usually lasts from 10 to 20 years. During that time, the outer skin is continuously exposed to wind, rain, and sunlight, making it a critical component for maintenance. Welded joints are essentially permanent. When cracks appear on the skin, the entire panel must be replaced, leading to significantly higher maintenance costs. In addition, routine inspections often require removing panels. If welding is used, this process is almost equivalent to stripping off the entire skin of the aircraft, a complicated and resource-consuming job. In contrast, riveted joints provide greater flexibility. The panels can be easily removed, and when damage occurs, only individual sheets need to be replaced instead of the entire structure. These three advantages have made riveting technology widely applied. An interesting detail is that the number of rivets on fighter jets and civilian aircraft is truly enormous. For example, an F-35 has about 750,000 rivets. Meanwhile, a large passenger aircraft like the Boeing 747 may require up to 3 million rivets. These numbers show the importance of riveting technology in aviation, not just a supporting technique, but a fundamental factor determining the durability and safety of the entire structure. Some may argue, if fighter jets have hundreds of thousands of protruding rivets, wouldn't that increase aerodynamic drag? In reality, the rivet system on fighter jets is divided into two main groups: protruding head rivets and flush rivets. Protruding head rivets include types such as semi-spherical head, flat head, truncated cone head, or plain flat head. These are mainly used in interior positions or areas with low aerodynamic requirements, where mechanical strength is prioritized over drag reduction. Flush rivets, on the other hand, are applied to critical positions on the aircraft's body, where aerodynamic requirements are high. This type helps reduce drag by about 3% thanks to the aircraft's skin being kept smooth and seamless. From the outside, aircraft might look like they have bumps, but when touched, it is almost impossible to feel the rivets. Today, on modern fighter jets, it is almost impossible to see rivet marks. For example, on the bodies of America's F-22 and F-35, rivets have nearly disappeared. In reality, they still exist, but in the form of flush rivets, which are highly concealable. After assembly, the surface is also coated with stealth paint, almost completely covering them. Notably, the rivet treatment technology on the F-35 is even more sophisticated than on the F-22. Because it was developed earlier, the F-22 mainly used radar-absorbing paint to cover flush rivets. Meanwhile, the F-35 was manufactured more meticulously. Rivets were installed flush, then polished flat, and coated with radar-absorbing material, creating an almost seamless surface. Each F-35 has about 50,000 rivets, and all must be perfectly flush with the skin to meet strict stealth requirements.
Not only the US with the F-22 and F-35, but also China with the J-20 and Russia with the Su-57 apply surface treatment measures to minimize rivet traces. However, their approaches are distinctly different. China's J-20 is the country's first fifth-generation fighter, with design priorities being stealth and long range. The J-20 uses many flush rivets combined with composite materials, estimated to account for more than 20% of the structure, then coated with radar-absorbing paint. Thanks to this, when observed with the naked eye, rivets are very difficult to detect. However, some close-up images have shown rivet marks clearly exposed, proving that China's surface treatment technology has not yet reached the same consistency as the US. Russia's Su-57 follows a different philosophy. This aircraft focuses on maneuverability and multi-role firepower rather than absolute stealth. Russia still uses quite a lot of traditional rivets, only applying flush rivets in important positions to reduce radar reflection. Therefore, at close range, joints and rivets can still be observed. This approach is pragmatic. Instead of investing heavily in stealth, Russia accepts showing some rivets to reduce costs, while allocating resources to 3D thrust vectoring engines, giving the Su-57 super maneuverability that the F-35 does not have. Besides the J-20 and Su-57, another important trend in modern fighter jet manufacturing is increasing the proportion of composite materials. On the F-35, composites account for up to 35% of the frame's weight, helping to significantly reduce the number of rivets needed. However, composites also have limitations, difficult to repair in the field and expensive to produce. Therefore, in load-bearing positions, rivets still play a crucial role. Not only the US, Russia, or China, but also 4.5-generation European fighters like the Dassault Rafale and Eurofighter Typhoon, thoroughly apply flush riveting combined with composite materials. The Rafale has more than 70% of its skin made from composites and aluminum alloys. Meanwhile, the Typhoon uses about 40% composites to optimize weight. This shows that, although not yet as invisible as the F-35, major aviation powers converge on several common trends: minimizing the number of exposed rivets, increasing the use of advanced materials, modern surface treatment techniques. Overall, despite the development of new materials and modern joining technologies, rivets still cannot be completely replaced. The reason is simple: they are cheap, durable, easy to repair, and extremely reliable. Future generations of fighter jets may use fewer rivets or hide them more cleverly, but they will certainly continue to exist in military aviation. From the MiG-25 to the F-35, from the J-20 to the Su-57, one thing remains unchanged: rivets are still present on fighter jets as symbols of reliability, durability, and flexible repairability. So what do you think? In the future, what other improvements might rivet technology on fighter jets have? Share your thoughts in the comments section. Don't forget to hit like and subscribe to follow the next analysis videos.